I'm Zhang from Beijing University of Post and Telecommunications. Today I'm going to present our work revisiting congestion control for lossless Ethernet. And this work was done when I was in Tsinghua University. Nowadays, RDMA is widely adopted in data centers. For example, Microsoft uses RDMA for its Azure storage. And over half of its traffic has been RDMA. To harness the full potential of RDMA, RDMA requires a lossless underlying network, which is usually guaranteed by link-level flow control, called PFC in lossless Ethernet. However, PFC comes with side effects, including head-of-line blocking, congestion spreading, and even deadlock. As a result, congestion control, which is usually used to avoid the frequent trigger of PFC, becomes a key enabler for lossless Ethernet at scale. So in recent years, several congestion controls have been proposed. For example, two early congestion control called distribution and timely. They essentially follow in the traditional lossy networks and use ECN or RTT as the congestion signal, and also use heuristic rules to adjust the flow rate. But they may suffer from the misleading congestion signal when the queue length is increased caused by PFC and may need long time to converge, so head-of-line blocking still occurs. While HPCC, another work, it resorts to advanced telemetry technique called INT to obtain high precision signal and introduce a larger overhead, so it may also sacrifice the throughput performance. Different from the above work, recently a work called TCD, which takes the approach of designing from scratch. It makes a new type in tailored congestion detection for lossless network, which is also our previous work published in CCOM 2021. By being aware of the on-off regulation of PFC pause and resume, TCD can distinguish between congested ports, congested switch ports, and victim switch ports. Thus, the flows contributing to the congestion point and flows only affected by PFC can be identified. For example, in this figure, the blue flows are the real contributors to the congestion point, while the green flows are the victim flows that are blocked in the switches. And the victim flows is also called undetermined flows. They will be marked with UE, and the congested flow will be marked with CE by using the ECN bits. However, although TCD can provide precise ternary signal for lossless Ethernet, but it still follows the heuristic rules as previous congestion controls, so making it essentially hard to achieve low latency and high throughput simultaneously. Basically, they just change the parameters of existing congestion controls. As a result, all existing words can only achieve suboptimal performance, including still suffering from head-of-line blocking or hard to achieve low latency and high throughput performance. So what is a desirable congestion control for lossless Ethernet? And in fact, congestion control can be decoupled into congestion detection and rate control. Congestion detection is the foundation for the all following rate adjustment, but rate control is indeed the core of achieving appropriate bandwidth allocation for each flow. Actually, both of them should be tailored for lossless Ethernet, thus achieving a high-performance congestion control for lossless Ethernet, which includes fast convergence to elevate head-of-line blocking, congestion spreading, and even prevent deadlock, and also achieve low latency and high throughput performance. So to design such a congestion control, the question instead we ask is, can we rethink congestion control, especially the rate control for lossless Ethernet, by taking full advantage of its intrinsic properties? To answer this question, and we start from revisiting the impact of PFC, which is indeed the unique mechanism in lossless Ethernet. And here we use an example to show that PFC can have more impact other than only introducing side effects. In this case, suppose the network pipe capacity is 5 packets, and the host will inject 15 packets into the network. So they will encounter congestion in the network. After congestion happens, and the queue will be start queuing in the switches. So PFC will be triggered to the upstream, and the pulse frame are generated to the upstream switches and with cascading effects. And thus the excessive packets will temporarily queuing at upstream switches. And in total, there will be 5 packets flying in the network pipe and 10 packets queuing in switches. And finally, all injected packets will be received by the receiver without any loss. And that is, with PFC, we actually have an end-to-end lossless network path, because no packet drop at immediate switches. So packet conservation gives a unique So PFC gives a unique packet conservation property to lossless Ethernet. The number of injected packets is equal to the number of ejected packets, which is also acknowledged by receivers. Besides, all injected packets, they are either flying in the network pipe or queuing at the switches. So the key implication behind packet conservation is that it empowers the ACK-driven paradigm, which is an old and classic concept, but it can become more powerful in lossless Ethernet. And we also conduct simulations to vividly demonstrate this. In this topology, H1 to Hn will generate concurrent bursts, so switch 4 and will have congestion at port P4. And F0 is the victim flow, and F1 is the congested flow. After congestion happens at port P4, the congestion will spread, and we can see in the left figure, the queue size increase 1 by 1. It's first port P4 and spreads to P3 and spreads to port P2. And also, the pipe capacity can be inferred from the in-flight packets, which is also the unacknowledged packet and the total queue size. And in summary, we can conclude that for congested flows, the excessive packets queuing in switches is exactly the the difference between the in-flight packets and the network pipe capacity. Besides, we also record the detailed ACK arriving pattern and arriving rate in this simulation, because the packet conservation property, the ACK are actually returned by receivers. So the ACK arrival rate can well imply the available bandwidth of the network pipe, which is also the maximum rate that a congested flow can pass through. So this is the power of ACK-driven in lossless Ethernet. And with the powerful ACK-driven paradigm, the remaining problem is that how we handle the headline blocking. Headline blocking is the unique problem in lossless Ethernet. And we also use the same simulation setup and study the queue occupancy of different flows and the impact of different rate control strategies. In this case, F1 is also the congested flow and F0 is a victim flow. The left figure shows the queue occupancy at a head of line blocked port. And we can see there are many queues, they are buffered. We find that if we only stopping the congested flow F1 enough long, the buffer can soon be emptied. That is, the headline blocking is eliminated very fast. So we can conclude that stopping congested flow sufficiently long can empty buffers as soon as possible. It is the fastest way for an end-to-end congestion control to eliminate the buffer. However, in another case, we find a port with more heavier headline blocking, and F1 is still the congested flow, F0 is a victim flow. But in this case, if we only stopping congested flow, we can find that there's still a buffer, and we cannot guarantee the headlamp blocking is eliminated. And in this case, there are a buffer of victim flows, and there are still risk of congestion spreading. So we conclude that as for the weakened flows, whether we should throttling them to help alleviate the headlamp blocking, it depends on the extent of congestion. So in summary, we have two key principles to build a desirable congestion control in lossless Ethernet. The first is because the packet conservation property, the ACK-driven paradigm should be renewed to infer the proper throttle rate and the precise number of excessive packets for congested flows. And second, to handle headlamp blocking problem, we need individual rules for different flows. First, stopping congestion flows sufficiently long is the foremost means we can do to suppressing the headlamp blocking. And second, weakening flows, they should adapt to the extent of congestion to alleviate the headlamp blocking and also do not sacrifice much throughput performance. So combining these two principles, we propose ACK-driven congestion control called ACC. We utilize the turnover signal provided by TCD and only resort to the information embodied in ACK time series to conduct corresponding rate adjustment for each kind of flow. Specifically for congested flows, we introduce a new state called source halt, which can actively stop its transmission. And in detail, the congested flows will employ a two-step approach. After detect congestion, it will first halt to wait for the exactly excessive packets to drain out and then matching its rate to the pipe capacity. And for example, in this case, after the sender sends packets in period T0, and it will receive packets in the next period. And it can figure out how many packets are acknowledged in T1. If congestion packets, then it will enter a source halt state without any data sending in this period. And the duration of T-halt is calculated by the number of the difference between in-flight packets in period T0 and the acknowledged packets in T1, and then dividing to the ACK arriving rate observed in the period T1. And this time is exactly the time of excessive packets to be drained at switches. And after leaving the source halt state, it will send at the rate inferred from the ACK arriving rate. And to calculate an accurate duration time of the source halt state, we also need to consider other issues like some in-flight packets are sent during period T1. So there are some details to modify the duration of the T-halt, and details are in our paper. As for the weakening flows, they will adapt to the extent of congestion spreading, and we use the indicator that the number of consecutive pairs with UE max. That is, the longer duration time of a victim flow, the larger extent of congestion spreading. And if it exceeds the threshold, it will decrease the inject rate. And for the uncongested flows, they just occupy the available bandwidth and increase the rate gradually at first and then aggressively. We implement ACC in Soft Rocket, which is a software implementation of RDMA, and we modify and add several core functions in the original processing logic at the sender and receiver. For example, we modify the check ACK function and initiate packet function, and we also add a rate pacer to enforce the rate. Basically, it will hold the packet until the expected transmission time. And there are only over 200 lines and 3 lines of code added in the sender and receiver, and over 100 lines of code added to the common library. We also built a test bed consisting of 5 hosts with 10 Gbps NIC, and 1 to-final switch. We also conduct simulations using NSDI packet simulator and using a fat trade network with 20 racks for large-scale simulations. And here is the summary of evaluation results, and we will briefly introduce part of them. They are mainly basic properties and FCT performance. And first, in the testbed experiments, besides ACC, we also implement disequation algorithm, and we found that ACC can achieve 25 fast convergence than disequation, which can only adjust the rate heuristically. And in an in-cast scenario compared with HPCC disequation timely, ACC can quickly eliminate congestion and maintain near full link utilization. This is because the halt time ACC can achieve a near ideal halt time without waste bandwidth. As for handling headline blocking, we use a challenging burst traffic scenario, and ACC can quickly empty the buffer, elevating the headline blocking, and it even achieves 1.75 faster time to empty the buffer than HPCC. And besides, ACC is resilient to deadlocks. We construct a deadlock-prone topology and run 50 times of simulations. Each time we generate random traffic according to the web search traces, and there is no deadlock, while disequation and timely suffer from deadlocks, which also confirm that fast convergence of congestion control in lossless Ethernet does help prevent deadlocks. And in large-scale simulations, we use this is part of the result. In a web search with 80% network load compared with HPCC, ACC can reduce average FCT by 29% and tail FCT by 40%. And also we compare with disequation plus timely and disequation plus TCD and timely plus TCD. Also greatly outperform them by 3.9 times and 5.1 times, which confirms that the tailored rate control in ACC is effective. In conclusion, ACC pushes precise congestion control in lossless Ethernet by unlocking its intrinsic packet conservation, so it can only use X to infer the throttle rate, excessive packets, and conduct accurate source hunting. ACC can well elevate special issues in lossless Ethernet and achieve lower FCT. And finally, we also believe that ACC can inspire congestion control or traffic management in other lossless interconnects, which also have the property of packet conservation. And that's all. Thank you, and I'm happy to take your questions.